Hello class. The purpose of this video is going to be to extend from what we've already learned in our class and kind of dig a little deeper into algebraic methods of finding extrema. We've already learned about extrema graphically, and now we're going to talk about absolute extrema. So remember, that's the highest or lowest point in a graph, but we're going to do so algebraically. And so the goal of this video will really be to find absolute extrema in closed intervals using something called the extreme value theorem. So before I begin, I just kind of want to make sure that we summarize what we've already talked about, many points we've talked about in class. So critical points, I will use CPs for short in the future, occur when the derivative is 0, but also when it is undefined. And that most students forget about the undefined part, but that's going to play a role in today's lesson. All extrema will happen at critical points. All relative extrema will happen at critical points. Now, absolute extrema can happen at critical points, but if they happen to be an endpoint, then that's why we don't just say all extrema. We refer to relative. But absolute extrema, if it's not an endpoint, will also be a critical point. But something really important is that not all CPs are extrema. You can have CPs, for instance, something like a cubic, where it flattens out, but does not necessarily have an extrema. Okay? So that's an example where a CP would not be an extrema. So the theorem that we're going to work with today is the following. If a continuous function f is bound by a closed interval from a to b, then f must have an absolute max and min, each at least once. So let's take a look at what that means. If I have a function and I draw it in blue, and I say, I'm gonna make it have a min here and a max here, and I'm gonna make it go over. Okay. The CPs are gonna be located whenever the derivative is 0 or undefined. In this case, we got a 0 derivative here, a nice horizontal line. Another one here. I happen to put it at -1 and also at +1. And so those are our two CPs. Now, you can see that this graph is not bound by a closed interval. It goes on forever. So in this case, our theorem would not be able to guarantee us that we would have absolute extrema, and in fact, we don't. It is a possibility that we could have absolute extrema even if you don't have a closed interval. For instance, if this were to come back down, let me use the right color. If this graph were to come back down, still put it in red. What that would mean for us is that the highest value of this function is in fact at x equals 1, and it's 3. And so this would have an absolute max, although it does not have an absolute min. So it is again a possibility that you get absolute extrema even if you don't have a closed interval, but that doesn't necessarily mean it will happen. But it could. So back to the graph we started with. In this case, if I say, you know what, I want to stop this graph. We're just going to stop this graph here at, let's say, -4. It's a good stopping point here. So I'm going to stop it there, and then I'm going to also stop it at, say, +4. And if we delete this other stuff, erase it, what you're going to see now is a different scenario. Let's get that cleaned up a little. So in this case now, our CPs are still extrema. That didn't change. But now our endpoints are also extrema. And so let's just kind of think about that. If I'm going to close the interval and the function is continuous, then I'm going to have a max or a min. There's just no other way to draw the function. There's no other way for it to happen. But our goal is going to be to determine if it's an absolute max or if it's an absolute min. And in that case, unless you have a graph, it's really kind of hard to see. In this case here, I have a y value of 2. And it is a max because it's higher than the points around it. And then here I have a y value of -1. Here I have a y value of 3. And here I have a y value of -2. So I'm basically going to need to compare these y values. I've got 2, -1, 3, and -2. And so what's going to happen when I don't have a picture is that I'm first going to have to identify where my critical points are and realize that my endpoints are potential extrema. So I'm going to have to then take both the critical points and the endpoints, and I'm going to have to determine their y values and compare. Clearly the highest y value in this case is 3, so that's my absolute max, and my lowest y value is -2, so that's my absolute min. And again, sometimes those will be the critical points, sometimes it will be the endpoints, but we're going to have to check. This happens also, let's say we had an undefined derivative. So let me draw you a graph of an undefined. Since I put arrows on this, again, right now, I'm not guaranteed by the extreme value theorem that this will have an absolute max or min. It does have an absolute min, but it's not guaranteed. So, but if we close it, say we close it here, and we close it here. Now the theorem says, hey, this function's continuous, doesn't have any gaps, jumps, or asymptotes, and it has a closed interval. It's going from -3 all the way to +4. So in this particular case, we're going to have an absolute max and absolute min. What we have to check are the CPs, which happen right where the derivative is undefined or 0, so it happened here. But we also have to check the endpoints now. And all we're going to do is take those 3 points and compare the y values. If we're over here at 4, this one's at 0, and this one's at 2, those are y values I'm writing, then clearly the highest y value is 4 and the lowest y value will be 0. And that's really the gist of it. You're going to have to check your find your CPs first of all. Where are they? Consider your endpoints and compare the y values. Remember, the y values always come from the original. So let's take a look at some examples. This is the same topic, but now we're going to look at an algebraic example. I do not have a graph of this, so I cannot just look at the picture and determine the answer. Instead, what we're going to do is we're going to do this algebraically. And here's the deal. As soon as you see your interval, which will always be given, okay, those are your first two potential candidates for your extrema. So this is not an ordered pair. This means from x equals 0 to x equals 4. So it's like 2 x's. I guess I can put x1 and x2. But these are automatically your first possibilities, okay? So what I'm going to do, I'm just going to build a little table to organize myself. Maybe I could do a better line. And here I'm going to put a 0. And then at the very bottom, I'm going to put a 4. And the reason I put it at the bottom is because those are our endpoints. This is my left endpoint. This is my right endpoint. But if there's any critical points in between, I'm going to list them. And I kind of like to go in numerical order. And then I'm going to have to compare the y values. The y value for 0, before we do any calculus, we can just plug that in here. And obviously that's going to be a 0. And I'm doing this so you realize endpoints, the y value does not come from the derivative. It comes from the original function. So I can put f of x here, if that helps. Then I'm going to put in a 4 and compute that value. So I got a -52 for that particular y values, for that x value. So I'll put a -52 here. So already I can tell this is my highest point so far, and this is my lowest point so far. But there might be something in between, and we got to check. So next, I'm going to follow the first step. Find the CPs of f of x. That's where f prime of x is 0 or undefined. So now I have to go over to the first derivative. And I'm going to take the first derivative. Here's pretty simple. Just a little power rule. 3x squared plus 3. Okay. And then I need to determine, is this going to ever be undefined? Because if it is, and I know that there are no restrictions in the original function, there's no undefineds, then if this comes out undefined, I have a CP. So I'm going to check and see that, nope, there's no possibility for anything to go wrong, like negatives in a radical or a 0 in the denominator. So then I'm not going to get an undefined possibility, but I could still set it equal to 0 and solve for x. Since I only have one x squared term, I'm allowed to move the 3 over, divide by -3. And this is only because I have one x squared term. If I had more than one, I'd have to do some factoring. Take the square root of both sides, and that tells me I'm going to get two possibilities. I'm going to get a +1, and I'm going to get a -1. Now, if I look at my interval only considers 0 to 4. So really, I'm not gonna mess with -1. That's basically not important to me because it is a critical point in this graph, but it is not part of my interval. So that means I only really have to check one critical point between 0 and 1, which is 1. And if we plug 1 into our function, we will get -1 plus 3, which of course is 2. And so judging by this table, this is where you get to be now at step 2 and 3. We're going to compare and identify. My highest value is going to be 2. So this is going to become my absolute max. And my lowest one is going to be -52. So that's going to be my absolute min. And remember, the actual maxes and mins are the y values. But we actually have their locations here at x equals 1 and at x equals 4. Okay. So I'm gonna do a couple more videos with other examples, but this is kind of the idea of how you do absolute extrema in a closed interval. So on the side here, you can tell I'm gonna do one that works with a little more complicated function, and I even have one with trig. So right when you're done this video, process, replay if you need to, and then move on to the next two. Have a good one.